Okay, so time to get back going again. We'll jump back into this lecture, and we're just about to transition into a newer type of bonding that's been recognized that for which fluorine is, can participate, and that's called tetral bonding. The name looks kind of funky. Tetral, tetrahedral, tetrahedrons maybe have something to do with it. Okay, so let's go ahead and start looking at the basic principles of this type of bonding interaction. Tetral bonds are a little bit more general than just a fluorine-specific substructure, so we'll describe the initial phenomenon first. In the general tetral bonding interaction, you'll have, there's my pointer, you'll have some type of atom. You can see the nature of those atoms there, all vertically, right? Yep. The single column there. They're tetrahedral in geometry, roughly tetrahedral, attached to 4 different groups. You have some type of a carbon-based group there, and through a charge transfer interaction, lone pair of electrons on some type of nucleophilic species can donate in. So what's going on in this system? You have a difference in electronegativity between your substituents and the heteroatom that generates partial cationic charge on the heteroatom, but you also have a sigma hole presented. And that sigma hole can interact with pi systems or lone pair of electrons in that charge transfer type interaction. We've seen similar interactions before. We have like a carbon iodine, carbon sulfur bond, like those are those type of halogen bonding interactions. In this case, the fluorine, the CF3 group, it's the fluorine atoms that promote formation of the sigma hole. Okay, so this is a unique interaction. You can see the CF3 group, I've redrawn that down on the bottom. The fluorine atoms being electronegative, pull electron density away from carbon. You get delta plus character here in the sigma star region, and then nucleophilic lone pair of electrons can donate into it. You can see the distances shown there. 2.5 to 4 angstroms. The angle, the geometries are pretty important here. In general, the angles are close to linear between whatever the nucleophilic atom is and the CR bond. That's close to 180. There's some deviance, there are outliers, but you want to be thinking of a roughly linear arrangement there. And these are not the strongest bonding interactions, still less than 2 kcal per mole, but that can still give you a benefit in a drug discovery campaign. So here's just a little bit of a visualization of what a tetral bonding interaction looks like, or the sigma hole specifically. When you have a model system, you'll see you have delta minus character in around the fluorine atoms and a little bit of cationic charge. This is for an aryl ring, a trifluorotoluene that has a hydroxyl group at the para position. If you have just a neutral species, trifluorotoluene, a little bit bigger of a sigma hole. And in this case, the sigma hole is a little bit more pronounced because the other fluorine atoms on the rest of the ring are further amplifying the size of the sigma hole. Okay. So that's what's going on there. There are a series of nice studies describing the physical chemistry behind this phenomenon, as well as demonstrating how it applies in drug discovery. So we can look at a couple of examples here. This is an example of a ligand that is making a tetral bond. The crystal structure that we've reconstructed and refined is shown right here. The distance of that interaction is 3 angstroms in this case. It's a nucleophilic oxygen presenting in to the sigma hole. You can see the angle there, not quite linear, but not far from it. And that's been computationally recapitulated through an analysis of non-covalent bonding interactions, in which you can see interactions in the modeling there. Okay, so these NCI analyses can be done. There's a little bit more information in the reference. But when you're looking at a crystal structure, trying to say, hey, am I able to exploit one of these rationally? Or if I have some type of a CF3 in my molecule, is it making this type of interaction? You have the general trends on the previous slide of what you should be looking for, the distances and the angles there, and you understand the basics of the physical phenomenon. Here's another example. Maybe first I'll say this was a side chain, a spartate presenting in, so you had an anionic functional group presenting in towards that sigma hole, and you can also have neutral species. So this is an example of a backbone amide that's nucleophilic at oxygen, forming a tetral bond with the CF3 group, and that's shown over here. Okay, you have the carbonyl lone pair of electrons presenting down in the distance there, 3.6 angstroms, a little bit longer, still nearing 180 degrees there, 167, that's still within the acceptable range. And again, an NCI analysis also demonstrates computationally that there's an interaction there between the carbonyl and the sigma hole of the CF3. Okay? So those can be exploited. You have to have the geometries right, you have to have the distances right, but that's also true for a lot of the other interactions we've been talking about. But this is a unique one for the CF3 group that can be exploited. So those are all favorable interactions, but fluorine, it can also resist certain functional groups. There are also fluorophobic environments for which it would be less favorable to present a fluorine or fluorinated substituent into this type of fluorophobic environment. So maybe we can summarize those briefly. Now, to summarize those, I want to come back to this original example from Francois Diederich's group. And I had mentioned before that there were certain derivatives that were less potent than others, than the core structure. And so that's shown here. Compound 1 is the non-fluorinated derivative. 2-fluoro, 2,6-difluoro, 3,5-difluoro. These are all less potent compounds. So you're presenting the fluorine into the wrong vectors, and further analysis identified certain reasons why that happens. So what should you not do? What are the fluorophobic type of environments that we should typically try to avoid? Well, if you have a CF bond and you have a lot of other electron density there, it's already a polar environment, you don't want the wrong ends of magnets presented towards each other. So if you have a CF bond that's electronegative and delta minus over on fluorine, and you have a CO bond that's delta minus on oxygen, it's not going to be favorable to have those things presented towards each other. Okay, you know that from playing with magnets as a kid. So that's not favored, as well as other dipoles that might be inappropriately aligned. So fluorine presenting towards pi systems. We know that pi systems typically have delta minus character in the pi cloud above and below the plane of the ring. Okay, for most systems, it's pi rich there. And you don't want the delta minus of that dipole to be presenting towards other anionic moieties, such as a pi-rich ring. Makes a lot of sense, right? So watch out, avoid that, and then the dipole alignment, that's another general principle that we should avoid. So here's an example of a study in which the group had been looking at some inhibitors of this enzyme. You can see that the structure here, the crystal structure, has some of the distances, and the disfavored interactions in this case have the fluorine atoms presenting into the pi systems. And you can see those here, distances here of 3.7 angstroms, that's kind of over the pi system. Here you can see 3.4, 3.7 angstroms, and again, those are systems in which the CF bond is kind of presenting in towards the pi ring. It's sometimes tricky to see in 2 dimensions, but you can further study this if you would like. Okay, so that's what's going on here. You have other disfavored interactions going on over there, and so those were all determined to be disfavored, and this was the main takeaway, the main message. Watch out for that CF presenting into pi systems. Okay. It's a hydrophobic environment. You can see all of the greasy moieties here, a couple phenylalanines, a tryptophan that's pretty greasy. But even though it's greasy and it's hydrophobic, you're presenting the fluorine at the wrong distances and the wrong vectors in this system, just based on the geometries presented in the pocket. Okay. So cautious about that. It can go the wrong way if you're pushing fluorine into pi systems. Okay. So those are some of the key things to watch out for. Things can get worse. We saw that initially in the multipolar interactions. Like we had that bin of compounds that statistically get worse when you put fluorine in there. Okay, that's another reason why here. So let's go ahead and look at some other types of molecular interactions for which fluorine is perturbing some other functional group and the interaction that it's making with a target. Okay, we'll see several different examples here, and we're going to be comparing maybe some charged species interacting with carboxylates. We'll also see how acidification of CH bonds can occur through fluorination, and then maybe we can drive affinity through a CH bond making an interaction with a Lewis basic set of lone pair of electrons from the target. So this is a really nice modern classic example of fluorination modulating the affinity of a drug to the target and being exploited to improve the toxicity of an important drug. So this compound itself is fentanyl. It's a mu-opioid agonist. It is a super potent compound. It is a painkiller. It's also one of the ones that's super addictive and super deadly. Okay. With the mu receptor, the respiratory depression is particularly deadly. They have reward. They're rewarding drugs, so the addiction is real to these things. But the respiratory depression is what's really problematic. So the drug structure itself has a basic amine. You can see the pKa there at physiological concentrations. That's going to be predominantly protonated. That amine is essential for engaging the mu receptor. So the electrostatic interaction between an active site aspartate and the protonated form of the drug drives affinity pretty significantly. Now, in the series of compounds presented in this paper, a series of fluorinated derivatives are introduced. And when you fluorinate, you change the basicity of the amine. So instead of having a pKa of just over 8, your pKa is now below 7. And below 7 means you're predominantly neutral under physiological conditions. So when you're neutral under physiological conditions, you do not have this electrostatic interaction that drives affinity for the receptor. So this compound is not going to have affinity for the receptor when you have the wrong pH, but under acidic conditions, as the pH rises, perhaps because of cell stress or some other thing going on in the cell, you can have increases in cellular pH. Then we protonate, then you have affinity for the receptor. So we now have a drug that will engage the receptor in more acidic media and more acidic cells. It will not engage the receptor as well in more alkaline cells. Okay. So that's a feature that was further studied and validated. I'll start over down here with mu-opioid receptor affinity. This is for the drug, the parent drug that just has a hydrogen in it. So that's the one that has a pKa just over 8. At pH 7.4, it's protonated predominantly. So the data that you're looking at here is potency data, Ki values as a function of pH, and for practical purposes, these are all the same values within air. Okay. There's no change of potency in these drugs as you go from pH 5, 6.5, and then physiological pH at 7.4 there. The tops, the bottom of these curves are within error. There's no change in the efficacy or potency either way. In contrast, for the fluorinated compound, you do see a potency shift as a function of pH. So at acidic pH, you'll see the Ki value, 7.3. See big error bars there, 2.6. So recognize there's big error bars in that measurement. At pH 6.5, you have essentially an equipotent compound. Again, because of the error bars here, these are like basically the same number. Okay. In contrast, as you go to neutral pH, at neutral pH, the fluorinated compound is less protonated. Remember, it's an equilibrium. So the amine is less protonated, and you start to lose affinity. You can see dropping down to about 18 there from single digits. Okay. So they're exploiting the difference in pKa between the two ligands to drive affinity in cells that are acidic, but lose affinity in cells that are less acidic. And in this case, under stress environments, certain CNS cells are acidic. So we can selectively get the drug to activate and engage the mu receptor in acidic cells, okay? So their in vivo efficacy was established in multiple models of pain, heat sensitivity, mechanical hyperalgesia, non-inflammatory and inflammatory pain models. There's a lot of different types of pain, right? The receptors, you know, when you poke yourself with a needle are not the same ones that are activated when you have a burn. Okay, and they're not the same ones if you have like arthritis. Okay, there are different types of pain, and different pharmacological targets might be better for different types of pain. Okay, nonetheless, this was evaluated in several different types of pain. It's important to think about the adverse effects, and can we modulate the adverse effects that can be come from peripheral activated mu receptors. So reward or addiction, that was modulated. We have minimal reward. We minimize reward potential when you have the fluorinated compound. These opioids, these mu opioids, they promote constipation. So you have mu receptors in the GI tract, and you take mu agonists, you typically get constipated. That you can see the number of defecations decreases when you're on the parent drug, but there's statistically no difference. They seem to be pooping perfectly fine when they have the fluorinated version of the drug here. Locomotor control is better with the fluorinated compound relative to the protonated compound, and they seem to, again, move around the cage reasonably well. They're not lethargic when you have the fluorinated drug relative to the hydrogen-containing drug. Okay. So they are generally safer. These are particularly important because this is what is toxic. This is what's deadly, what's lethal for these drugs. The respiratory depression, losing oxygen in your system, decreased heart rate, that's what kills people when you take too much of these things. And this compound did not affect those as much as the parent compound. Okay, so cool story there. Hopefully more might eventually come from that strategy. But the mu receptor is really tough to target and target well, even though we have several drugs that do hit it. So another fluorine-induced phenomenon is the acidification of geminal CH bonds. So the acidity can actually replicate in some conditions the acidity of a phenol. Okay. And that's going to be the sigma withdrawing effect of the fluorine atoms pulling electron density away from the carbon. As a result, the carbon, it still wants electrons, so it's going to be pulling electrons out of the CH bond towards itself. And that's the nature of the acidification. It has been studied in a couple of systems. Some say it's a stronger interaction, some say it's not quite as strong. So there's disagreement in the literature about how powerful is this interaction. Nonetheless, you can see in the OH bond, you have your oxygen, you have your cationic hydrogen. Here we have our CF2 that has a lot of delta minus character, and the corresponding hydrogen would be out over in this space over there. Okay. And you can see the blue coloring and the red coloring in similar locations in those two structures, in those two computational models. And these have been further studied. One estimate based on this really cool supramolecular arrangement estimates the energy associated with the OH hydrogen bond to be about 3.5 kcal per mole. And in this case, you have a nitro group making an intramolecular hydrogen bond and an intermolecular hydrogen bond there. you can see this network having about 3 kcal per mole in energy. So this estimate says they're pretty close in hydrogen bonding potential and hydrogen bond strengths. One other thing to think about here is other changes in the molecule. So even if maybe you lose a little affinity, can you still have a better molecule overall for your discovery process? Let's think about the rest of the pi system. So if we're thinking about oxidative metabolism here in this case, we have a more pi-rich system with the phenol, and the CF2 is pi deficient. Maybe you'll have less arene oxide formation, less hydroxylation of the aromatic ring using this substitution relative to that substitution. Maybe that compensates for a little loss in potency. In contrast, or in addition, that hydroxyl group can undergo the conjugative metabolism. It's nucleophilic. You can conjugate on sulfates and glucuronides and other things onto this substructure, this phenol. You're not going to do that over here. This is not going to undergo conjugative metabolism. Pretty powerful difference for pK properties, perhaps, if you use it properly. Okay. It doesn't always work. You can't always get a phenomenal hydrogen bonding interaction with this substructure, but sometimes it works and works great. So, a second study, a more recent study here, suggests that this is not actually a very strong hydrogen bond donor. In this study, they used that A NMR strategy that I had mentioned previously. I said there's a mathematical equation I'm going to show you. You just have to wait for it, and here's the equation. The paper that has this equation, description of the assay, is on the other slides that we had before. Okay, but even if you go to this this paper down here on the bottom, they cite the right one anyways. Okay. So the strategy for measuring this, again, involves measuring the difference in the shift of the proton when you measure the NMR in DMSO relative to chloroform. Okay, and the difference in shift estimates how acidic that hydrogen bond is. And you can do that with phenols and alcohols, but you can also do it with some of the CF2 bonds. And we'll look at a little bit of the data there. So in the phenols, here's A values suggesting that these are reasonable hydrogen bond donors. Just for a comparison, if you have like toluene and you know, what is this, ethyl propylbenzene here, you can see negative A values. Those don't hydrogen bond well with DMSO or chloroform, right? But when you go over to the CF2H on the other side, you'll see the magnitude of the A value is significantly lower than the magnitude of the A value over here, about 10 times weaker. Okay, so this estimate is saying, these are pretty minimal. It's not very acidic. It's not very good for drug discovery. Nonetheless, they can have profound effects. And so here's a series of molecules that has progressed into a clinical candidate. In this early series, we have an NAS3 protease inhibitor. You saw one of these other molecules when we were looking at the metabolism. We had a big heterocycle here. All of this substructure is the same. You actually had this linked over here. We did geminal difluorination, and then we also had a moiety, I think it was dangling off of this position here. That was the vinyl group, and then we looked at a bunch of fluoroalkyl derivatives coming off of that position. But the target here is the same target as we had already looked at. And again, when you look at the slides and look at the drugs, like scream out, like, yeah, these are the same target, okay? The NS3 compounds, like, they all look very, very similar to a medicinal chemist. Okay, so in this series, we're looking at inhibiting replication in a biochemical assay and then a cellular assay here. So that's why you see more potent compounds in the biochemical assay relative to the cellular assay there. The specific series of compounds will have a cyclopropylmethyl, difluoromethyl, and trifluoromethyl. The potency of the compounds increases over 10-fold as you go from methyl to the CF2H. The CF3, when you put the CF3 in there, you lose potency. You know, no beneficial interaction relative to methyl. when you go to CF3. Okay, so there's something about having a CH there that's useful, that's helpful, and this data is also replicated in the cellular activity. And the crystallographic data indicates or suggests a CH bond. That CH, that's the CF2 right there, and then this is the CH bond presenting down and making a hydrogen bond. I didn't remember off the top of my head, that's 2.5 angstroms there for the distance between that CH and the carbonyl. Okay, so within the distance you would expect for a good hydrogen bond there. And so maybe in some cases it can be useful, it can be beneficial if you get the distances right and you get the angles right. Okay, so it can be used, it can be exploited. Again, the model systems seem to disagree on how powerful it can be. The medchem evidence suggests it can be useful. Okay. So we're going to look at another really, really unique example of model system. Yeah?
But sir, in previous slide, there were also chances to get that bond, that CF3, where it is attached to that cyclopropyl ring, that is rotatable, right? That bond is rotatable. So
Yeah, so you're saying if this is CF3, that's, okay, go ahead.
Here there were chances that fluorine can have an interaction with that carbonyl as well.
Yeah, I think what's going on here, so I'm going to stay on the mic over here, try to talk from over here. So the CF3, if you had a fluorine here, that's actually closer to the carbonyl than it is to the carbon. And if you put the CF3 presented towards the oxygen of the carbonyl, sorry, it's close to the oxygen of the carbonyl. So if you present the CF3 towards the oxygen, you have delta minus character here and delta minus character on the oxygen, and that's repulsive, and that's recapitulated in the data, or the data supports that. When you go from a methyl to a CF3, it's worse. Okay, now if you had a dipole interaction, or the multipolar interaction that we were talking about right at the beginning, the first interaction we were talking about, you would need a fluorine atom closer to the carbon, not closer to the oxygen. Okay, so think about that. If you're like this, that's bad, but if you place it there, it's good for those multipolar interactions. And I think that's what you're thinking about. Okay, is that fair? Okay, so the distances matter, the angles matter, the geometries matter. You can take something repulsive and make it attractive. Maybe if they could reach a little bit deeper into that pocket. I don't know what's closer to us, like how tight that pocket is. I don't know what else they did. But this, progressed on to a clinical candidate. So, yep.
About this, again, I have one doubt and also a comment because I think somewhere I read that, and also I mentioned in my talk that, or it is actually mentioned by an author in the paper because I am not experienced in paper, that mostly the driving interactions are hydrogen bondings, the typical hydrogen bondings, and these are the add-ons.
These are the what?
Add-ons, which adds to the overall the stabilization of that receptor ligand interaction. So, because for example, in this interaction there could be adjacent hydrogen bonds which has already locked.
Oh yeah, absolutely.
And now your CF and because now there is no much room for the molecule to turn and make conformational change so that they can because going from near oxygen to near carbon in the carbonyl could be possible by a conformational change, but now that is not being allowed because of the other interactions in the molecule.
So you are relying on the rest of the system. Is my clicker? Okay, there. So you are relying on your heterocycle and this over here and this stuff. You're relying on that to drive affinity, right? We're already at a 10 nanomolar compound. There are a lot of other things that are well positioned in this molecule that are driving the initial affinity. And this is gravy. This is great to get this jump, this boost, but all the other interactions are giving you a 13 nanomolar compound to start, right? And I think that's where you're going. This is late stage fine tuning, improving interactions, but you have to have everything else set up so that you can see these types of boosts later on. If you're using this type of interaction to drive affinity from the outset, it's going to be tough. Yep. Okay. So this is a really fun story on fluorinated ketones. Fluorinated ketones have unique interactions with biological systems. And in order to understand this, we need to go back to some really, really basic physical organic chemistry, ask the question, what happens to carbonyls when you have electron withdrawing groups attached to them? So we're going to, for teaching purposes, we're going to just think of like an aliphatic or diaryl ketone and what happens when you put a strong electron withdrawing group next to it. Okay. It turns out that the strong electron withdrawing group prefers to, it encourages the carbonyl to rehybridize. So you go from an sp2 state to an sp3 state. Okay, and that happens because the sp3 hybridized state allows electrons to distribute towards the electron withdrawing group. Okay, this is a phenomenon that was described by Bent. Basically what's going on here is when you have sp2 hybridization, the contribution of this bond here from the carbon atom, it's an sp2 orbital, 1 part s, 2 parts p, a little bit shorter. The carbon is a little bit more electrophilic. The carbon in CsP2 is pulling its electrons, holding its electrons a little bit closer to itself. When you rehybridize to sp3, now we have 1 part s, 3 parts p. Those orbitals are a bit longer. The carbon allows the electrons to drift closer to the electron withdrawing group because those orbitals are a little bit longer, a little bit bigger. Okay? So it's a better electron donor into the sigma bond when you have a CsP3. In this case, we have CsP2, it's more electrophilic. We have an electrophilic carbon next to an electron withdrawing group. They're playing tug of war for the electrons. There's an electronic argument going on between those two. They both want the electrons more. Again, rehybridization allows the carbon to share its electrons better with the electron withdrawing group. Now, the electron withdrawing group, for purposes of this class, CF2. It's going to be a fluorinated group. And so let's go ahead and think about what's going on. In order to go from CsP2 to CsP3, we need some type of nucleophile to add in. It could be an alcohol, it could be amine, it could be water. Okay. When that happens, that's going to require the attack of that moiety onto the carbonyl. Okay. When you have the carbonyl and you're thinking about the LUMO of the carbonyl, the HOMO-LUMO energy gap is going to be smaller when the alcohol attacks the more stabilized carbonyl, the carbonyl that's lower in energy, that has a lower LUMO. Okay. So that's one feature. There's a kinetic preference for nucleophiles to attack these fluorinated ketone derivatives. But the other one that I was telling you about before is a thermodynamic argument, in that there's a difference in the hybridization of the two orbitals. The CsP3 hybridization state allows electrons to flow towards the delta plus more readily. Okay, so it turns out that this substructure has been exploited for biological probes and therapeutics regularly enough. I'm going to put a couple of examples up on the next slide that are going to involve proteases, serine proteases, and aspartate proteases. Serine proteases, they cleave peptides, right? And the catalytically active species in a serine protease, it's going to be a nucleophilic serine hydroxyl group. Now, there are going to be other amino acids in the enzyme that help activate and stabilize the transition state. So again, think about the hydroxyl group attacking the carbonyl. When that happens, you generate the tetrahedral intermediate, and then you need stabilization of this species. And that's what some of the other residues in the catalytic pocket are doing. Ultimately, collapse of the tetrahedral intermediate will cleave off an amino acid, and you can ultimately regenerate the catalyst system. And in this case, you can use fluorinated peptidomimetics to make reversible covalent inhibitors. Reversible covalent inhibitors. What does that mean? Okay, so in this system, you can see how the CF2 group is introduced into the ketone. When the serine hydroxyl group attacks, we've now made a covalent bond between the drug substance or probe and the enzyme. That transition state, that tetrahedral intermediate, will be further stabilized by the other residues in the active site. But the drug itself cannot float away until the tetrahedral intermediate collapses. But when it collapses, it cannot cleave. You don't have the carbon-nitrogen bond here. See here? When we close that tetrahedral intermediate, we kick off the amino acid. In this case, you're kind of stuck there. Okay, so it's a covalent inhibitor, but it's also a reversible inhibitor. It's a really cool strategy for going after serine proteases. Now, there are other classes of proteases, and some of those can also be targeted by these fluorinated peptidomimetics, these fluorinated ketones. And aspartate proteases are also another example here. So in aspartate proteases, you have different amino acids in the catalytic site responsible for activation of the correct peptide bond. And so in the aspartate proteases, you have two aspartates. One of them is making a hydrogen bond with the appropriate site of the peptide that you're trying to activate. The oxygen is bridging over to water that bridges over to the other aspartate. So what you have is a highly organized system in which we're activating the carbonyl, but also recruiting water and presenting water at the right vector to attack the carbonyl. Okay, so you have activation of the substrate here, you have activation of water and recruitment of water. And when water attacks the carbonyl, you make a really nice tetrahedral intermediate. Look at the beautiful stabilization, hydrogen bonding network there. A really nice organization. Nature figures how to do really cool things sometimes, and this is one more example. Collapse of the tetrahedral intermediate ultimately cleaves the peptide at that site, and you still have the aspartates there. Now, the fluorinated peptidomimetics can also inhibit these enzymes, but in this case, it's not a covalent inhibitor. It's an inhibitor in which the substrate will still get recognized by the enzyme. It can still get activated by the aspartate, and the delivery of water generates this really beautiful network there. And that's a stable network. It cannot cleave. Again, you don't have a CN bond here. You have a CC bond. And so you kind of get stuck in this state in which you have the CSP3 hybridization that the fluorinated ketone wants anyway. It's more stable in that hydrate state. And then you have the really nice hydrogen bonding network that can really drive affinity. Okay, so let's see a couple of examples of how this plays out in biological probes. The first series is acetylcholinesterase inhibitors. Acetylcholinesterase is a serine protease. The endogenous substrate is shown here. The affinity of the substrate for the enzyme in this case is heavily driven by the charge. There's an anionic residue in the active site of the enzyme that recruits this cationic amine. If you get rid of the cationic amine, you really lose affinity, big time, right? Yeah, we're nanomolar, 300,000 nanomolar. It's not very good, right? So if, in this case, we've taken the charged amine, we've replaced it with a T-butyl group. We can regain a massive amount of affinity by introduction of fluorine atoms on either side of the carbonyl. If we put it over here on this side, a trifluoromethylketone, look at that change in affinity. Wow. And if you have two fluorine atoms on the other side, you have this internal difluorinated ketone, you drive affinity even further. Now the difference is that there's a little bit of steric congestion. We have the bigger CF3 group on the side. The enzyme typically recognizes it as an acetate. The acetate has a little methyl group right there. Okay, so the pocket isn't outrageously big. The CF3 is just like, it's a little too big to fit in there perfectly. But if you bring the fluorines back over to the other side of the enzyme, I mean, look at that affinity, like 300,000 to 1.5, 1.6 with 2 fluorine atoms. That's pretty dang cool. Okay, let's look down at the second example. The second example, it's still cool, maybe not as cool, but it's still pretty cool. This would be the example of a couple of probes and the some data in terms of how they engage aspartate proteases. I'm going to start over here with this one. This is the fluorinated ketone. This one over here is an alcohol, and I'll do a quick comparison with that one in just a minute. So for the ketone, again, the aspartate mechanism, let's quickly review that. Here it is. We're thinking about this type of an interaction there, okay, that type of a network, and the fluorinated ketone can facilitate that network. When you go from the HH ketone to the difluorinated ketone, look at the difference in potency there, 134 to half. It's pretty good. It's pretty good change when you can use that properly. In the other case, you actually see that the fluorinated compound is less potent. What's going on there? Well, this is a case for which instead of a ketone, we have a hydroxyl group. Now that hydroxyl group, I'm going to go back a slide just to remind everybody what's going on. If you have a hydroxyl group at this position, we can only make one of these hydrogen bonding interactions. We can only get one of those. We can't get both of them. Okay? So if we have a single hydroxyl group, we can still ask the question, well, if we have a CF2, how is the CF2 going to perturb these types of interactions? Okay. And you know this. We talked about the basicity and acidity changes that occur. So you can go back to those tables if you want, or you can just think for a minute. Well, if we have a hydroxyl group, the OH bond is going to be more acidic. Okay, if it's more acidic, that's the hydrogen bond donating potential. It's going to be better, but we're going to be less basic for the lone pair of electrons. And if we're losing affinity, maybe it's the loss in basicity of the lone pair of electrons here in engaging the receptor, or the you know, that hydrate-like form that we saw in the previous slide. Okay, so if we have a ketone, we're rehybridizing, really beautiful interactions there. If we're at the alcohol, we're just perturbing the acidity and basicity of that functional group. In this case, you lose affinity for the receptor. Okay, cool example. Basic principles explain it all, right? You just go back to those perturbations that I kept beating into you early on, and now it hopefully helps. It pays off eventually. So these types of this substructure, this moiety, has been used to modulate a wide variety of different enzymes. You can see lots of disease states. You can see serine aspartate proteases, other popular targets that have been drugged over the years, diuretic type activity. This is a really fun one. I should probably make an example of this one for like the tutorials. But this is a beautiful one for conformational control. Because what happens in this case is you have an alcohol there, and the nucleophilic alcohol will attack the carbonyl and make a hemi-acetal, hemi-ketal type substructure, and that's stable because it wants to exist in the CsP3 form there because of the fluorine atoms. So it's a control element for having this thing cyclized down into a ring. It's pretty cool. Okay. So I have one more phenomenon to talk about in this series of examples by which fluorine can modulate the reactivity between a small molecule and a biological target. And it's going to be in the area of phosphates and fluorinated phosphate mimetics. So phosphates, super important for biology, chemical signaling. Kinases transfer phosphates from enzyme to enzyme to enzyme for signaling. We know phosphates can activate nucleosides. The nucleosides themselves, so that primary hydroxyl, need to be phosphorylated and then diphosphorylated, triphosphorylated because before they can get polymerized. We saw those cyclic nucleosides, cyclic AMP, cyclic GMP are important chemical messengers within the body. Those have a phosphate bridging two nucleosides. Okay. Phosphates are super important. There are enzymes that put on phosphates, the kinases. There are also enzymes that remove phosphates called phosphatases. They can also hydrolyze under the right conditions, okay? So phosphates going on and off of biological molecules has a really, really, really profound effect on physiology, biology, cellular enzymology. Okay, so that these enzymes can go on and off. They have certain acidities associated with loss of one or both protons. You can see the pKa's there, very close to phosphoric acid. Now, in order to generate biological probes or therapeutic candidates for which you can engage the enzyme with a phosphate-like substructure without having the liability of that phosphate falling off, we can use phosphate mimetics. And one common strategy is to introduce a carbon-phosphorus bond. That carbon-phosphorus bond can't cleave. And when it engages the enzyme, you still have these three the two acidic OHs, the phosphate, and then a third oxygen there. So you can see how maybe in the pocket of the enzyme, regardless of what pH you're at, you might be able to mimic the interactions. Now the challenge here is that the pKa's are different. Oxygen be more electron withdrawing, carbon be more electron donating. You get roughly a log difference in pKa, so they won't be anionic or dianionic under the same conditions. But we can use fluorine to modulate pKa's. Electron withdrawing group, that effect can acidify the OHs on the phosphate. So I'll introduce briefly a couple of different derivatives. You can use a monofluorophosphonate that brings the pKa very close to a phosphate itself. That would be what we call an isoacidic variant. If we really need that phosphate to have the same charge as this one, we can use a monofluoromethylphosphate. Now, this is a stereo center. You have to be thinking about two different isomers. Maybe that's important for your target, maybe not. But you have to watch out for the stereochemistry there. Now, this oxygen introduces a dipole into the molecule. And if you need a molecule for which you need the similar polarity overall, you can use the CF2. The CF2 mimics the dipole of the oxygen better. The carbon-fluorine bonds present at the same vectors roughly as the lone pair of electrons. So that's what's going on there. This is an isopolar mimic. It's a little bit more acidic. We have an isoacidic mimic, and then the CH2. Remember, fluorine atoms are really big, right? They're not H's, right? They're bigger than H. We established that on slide number 1 of this entire thing, okay? So this is a bigger functional group. If you want it to be isosteric, the CH2 is the one that mimics the size of the phosphate better. Okay, so you have a couple of different derivatives there, and these have been used pretty broadly in chemical biology. A lot of times if you're trying to take like a phosphopeptide, you don't want that phosphate to come off, and you just want to see the activity, like when it's phosphorylated, what happens. This is a great strategy. Okay. So, hopefully the key points have become apparent. There are several examples that we've looked at, but you can use fluorine to modulate acid-base chemistry, and that can subsequently affect engagement interactions with charged residues and molecules. You can also modulate other interactions by fluorinating and perturb those interactions. Let's come into the end of this lecture. We're also very close to the end of like all the coursework type lecture. As much as possible, I'll keep reminding everybody to be a master of the physical organic chemistry and think about the really basic principles and how they apply and how they influence all of those drug-like properties. The drug-like properties are ultimately what you're measuring to say, is this compound going to be good enough to put in my cellular assay, in my in vivo assay, and ultimately someday a clinical candidate, hopefully, from some people in this room. This is really important stuff, but the basis for everything we're studying here is physical in nature. So if there's like one key message, make sure you're really strong in physical organic chemistry, understand the molecular interactions, think about thermodynamics and kinetics and all those things. It's going to apply in biological settings further down in your careers, okay? So, that's it for today. I think we're breaking for lunch. It's 12:25 and we were kind of shooting for 12:30, so I think we're close enough. And when we come back, it's going to be more of a scientific lecture, and I need to go make a boatload of adjustments to my slides because it's a 2-hour time block, and so it's going to be an interesting one. So, anything else? What time should we be back? Or
Yeah, so I think we have some